I'm Mike Rodriguez, and today I want to talk about rules engines. And I've been using rules engines for about the last 4 years now at Cerner in the healthcare space. And today I want to talk about what rules engines are, what problems they solve, and how they work. Okay, so throughout the talk I'm going to be using Clara rules to demonstrate. And Clara rules is an open source rules engine. It's written in Clojure by Ryan Brush, who also works at Cerner. We've been using it and contributing to it for about 2 years now, and we use it in production. We used to use Drools exclusively before that, and the good thing about Clara is it's been able to perform competitively with Drools as we've transitioned, and that's been a really important benchmark for us because we try to run thousands of rules against data sets that sometimes have 100,000 plus data points within them. So we're going to talk about Clara a little bit more as we go. So the rules engines I'm referring to today will be the forward chaining inference engines. They're derived by some variation of the Rete algorithm. Paula yesterday in the Naga talk discussed the Rete algorithm a little bit, and today I'm going to have a little bit of more discussion on it towards the end, just as it applies to Clara and in the examples that I have today. And so the Rete algorithm was around in the 80s, and most of the rules engines today, most of the forward chaining style ones, are based on some variation of this algorithm, and that includes Clara rules. So when we're talking about rules engines, first let's talk about what a rule is. And a rule is just an if-then construct. And we have a left-hand side and a right-hand side. And the syntax I'll be using today is going to divide the two sides by this arrow, this symbol arrow. So the left-hand side is the if side of the if-then, and the right-hand side is the then side. And so a rule is considered activated when all of the left-hand side conditions are satisfied. And then when a rule is activated, that just means that the rules engine, it's eligible to be fired by the rules engine. And firing a rule just means to execute that action on the right-hand side. So rules are evaluated against a data set. And this data set's stored in memory. We usually call it the working memory. And every data point within working memory is called a fact. So the right-hand side action of rules, they perform arbitrary side effects, but the important one and the most common is that they can update the state of working memory. And so they can insert new facts, they can retract and update existing facts. And since they can do that, they can influence the behavior of other rules because the changes to working memory will influence if other rules are true or false. So when you compose rules together, you can form more complex conditional logic based on this. All right, so the basic job of the rules engine is just to evaluate this set of rules against this working memory state. And the basic evaluation is like this is a loop, this cycle, where the rules engine determines which rules are activated. It picks one of them and fires that one. And then it just reevaluates to see which rules are now activated, because things might have changed, because working memory might have changed. And eventually you run out of rules that are activated and the loop stops. And once you stop, the rules engine's in some sort of steady state at that point, and that's when you would query on it to figure out what happened, what facts are involved, and what information was derived during the firing of the rules. So I want to take a couple minutes to look at Clara rule syntax, because I'm going to use some of the syntax as we go and some examples later on. So starting off just real basic, here's a rule. Def rule defines a rule, it's a macro. The rule A, this is saying the rule name is rule A. This rule is not doing anything useful or interesting, it's just about the structure. There's a left-hand side and a right-hand side. They're divided by this arrow symbol, like I showed before. And this rule has one condition in it, and conditions are always surrounded by these square brackets, like a vector. And so a rule is, this condition here is, a fact matches this condition if it has the type of fact type 1, that's what that means. And then it also has to satisfy all these constraints that follow the fact type. And here I have this constraint fn x some value. And I'm just putting that there to show that it's any function. You can use any chain of functions you want right here. And your functions are just going to act as a predicate. So nil and false are false, everything else is true. And the x is referring to the field named x of the fact that we're talking about. So the Clara rule syntax does allow you to access fields directly by their name. But other than that, the function call is natural. Like some value is just a keyword. And I'm just putting it there to show that calling functions is how you expect function calls to work. But the second constraint is special. And so any symbol you see that has a question mark just starting it is what we call a variable binding. And what variable bindings are pretty much like a local variable that can be used throughout the whole body of the rule. And so y binding here is being bound to the value of the field y. And you can see I'm using it in the right-hand side, so it's like locally scoped. And when this rule fires, so the right-hand side, you see insert, that's a function call, and Clara, that mutates the state of working memory, so it's inserting a new fact into working memory. And you see that I'm just making an object called thing A, but it's using that Y binding value as we derive the new information. So looking at another rule. This one's pretty much the same rule as the first one. I just added another condition onto it to demonstrate another feature. So looking at the second condition, I have join fn, which again, that name doesn't mean anything. It could be any functions you want. But the arguments to it are important. Taking y and z, but notice that y is a variable binding, and that it's bound to the field y of the fact on the first condition, but z is a field of the fact from the second condition. So we're putting two facts together. So we're creating a join sort of logic on those two facts. So this is how rules can express joins like in relationships between facts. And this rule would be activated and it would fire for every possible join between the two sets of facts. I also demonstrated a little bit more syntax in that second condition just to show it. It starts off with this variable binding called fact2, and then this arrow that points to the left. And all that means is it just says bind this fact2 variable to the entire result, the entire fact that matches this condition, instead of just a field at a time like I've showed before. But other than that, that's just a normal variable binding. You can use it the same way as the other ones. This rule, the only thing special here is the second condition is a negation condition. They start with the keyword not, and then have a nested condition inside of them, and this is going to be what you would expect from negation. It's true when the nested condition is not satisfied. So it's checking for non-existence of a match. And then one more style of condition I'm demonstrating with this rule is what's called an accumulator condition. It's the second one. It has the keyword from in it. That's how you can tell it's accumulator. And after the from is a nested condition. Before the from is an accumulator. And what these conditions do, is they take every fact that matches that nested condition at once, hand it to the accumulator. The accumulator produces some value based on that. And you can use that aggregation value instead of just the separate facts that made it up. So these are important when you want to have a condition that reasons about a whole set of matches at the same time rather than one at a time, like the normal rule matching goes. Using a variable binding called all, that just binds to that result of the accumulator, and then I can use it in the right-hand side or anywhere else you could usually use variable bindings. The other thing is ACC all, that ACC / all. That's just a built-in Clara accumulator that takes all the facts that matches, and it just makes a collection of them and returns it. So it doesn't really do any work besides just pass the collection along. There's also more interesting things you can do with accumulators, like find the best match of all the matches by whatever definition of best is, such as maybe the newest one if you're looking at dates. So any kind of arbitrary aggregation operation, and they're customizable. You can write your own accumulators. So the last kind of important feature of the rules engine that I want to talk about is what's called the truth maintenance system. And I'm just going to explain what that is just by looking at an example. So there's two rules here. We have find A and find B. And find A, it's satisfied whenever we have a fact of type A. And when it fires, it inserts a fact of type B. Find B is like the mirror image of it, but it just looks for facts of type B instead and inserts the facts of type C. So if we had working memory with nothing in it originally, and then we add a fact that I'm going to call A1, which has type A, then we fire the rules, then find A would be satisfied. And then we would insert a fact of type B, I'm going to call that B1. And then when that happens, the find B rule is satisfied. So then we will create a fact of type C and call that C1. So after we inserted A1, we have A1, B1, C1. So then let's say that we want to retract A1 at some point later. Either you can do this like in another rule, maybe that isn't involved here, or like the external application could retract it. So either way that happens, if we're retracting A1, what's going to happen by the truth maintenance system is it's also going to retract B1 because it remembers that B1 was inserted because A1 existed, and now A1's gone, so B1 has to be gone too. And transitively, the same thing's going to happen to C1. It was only supported because of B1, and B1's gone, so we don't have C1 anymore. So retracting A1 alone retracts A1, B1, and C1. The reason I'm bringing this up as an important feature, and most rules engines have it, including Clara, is because it allows you to write these complex sets of rules where you don't have to worry about the order that they fire and the way they interact with each other. Like You don't want to be concerned that if one fires too soon that it'll make another rule false that you've already fired. So not having to deal with this problem of when things are happening. Instead, what you get is after the rules are fired, you know that the state of working memory is going to be logically consistent with the left-hand side conditions expressed by all of the rules. So with that out of the way, I want to try to drive some reason behind why you might want to use a rules engine. And the two main big points I say that might be of interest is you can declaratively express complex conditional logic. And the other thing is the rules engine tries to be efficient in avoiding recalculating this intermediate states that are involved in different paths through the logic. And I'm going to use an example and kind of walk through it so that we can see some kind of concrete visualization of what might be happening, how the rules engine might help. So my example problem is a really simplified version of just looking for hypertension, which means high blood pressure. And the rules here are going to be that a person's hypertensive if they have a blood pressure that has a systolic value greater than 140 and a diastolic value greater than 90, and it was taken in the last year. So that's what you would call greater than 140 over 90. The other stipulation I'm going to add is that blood pressures aren't just going to come into the system paired up already. Instead, we're going to get individual data points on a result model, and they're going to be either of type systolic BP or diastolic BP. And we're going to have to put them together to get valid pairs before we can test the values. So to get a valid pair, you join them by having the same day. Okay. So I'm going to start off with using a function composition style approach. Just what I mean by this is just kind of your standard, how would you do it, and some Clojure code kind of approach. And you might end up with something like this. I'm pulling out all the pieces to make it really clear what's happening. So I have these kind of helper functions, and then I have this hypertensive function that really deals with the actual problem statement. And so the hypertensive function, you can see, just composes everything together in the end. So my helper functions are little things like I have results and I have a BP type, so I just want to get the results that have that BP type. Then we have a function that combines blood pressures. It takes systolic blood pressures and diastolic blood pressures and puts them together. And then we have a function that can take blood pressures and narrow it down to only the ones that are within the given period relative to some current date. And then a value testing function. But then the hypertensive, the actual function implements the logic, just threads them all together. And that's pretty common. You have all these simple composable pieces, and you compose it all together to deal with your problem. So the only thing that's interesting at the end, we just look for one that has a value greater than 140 over 90, which was our original problem. So this is straightforward, and this doesn't require any further thought, really. But usually what happens is these problems don't stay this easy. Like, I probably don't only want to ever know if the person's hypertensive if I'm trying to do some kind of figure out some information about a person's data, like healthcare. So I might want to ask more questions as the system goes, as time goes on. So I might have new logical branches that are related but not the same as the one I have here, the one I started. And then also you might want to just make it more advanced with how do I find blood pressures. It might get more complicated than what I have. This is pretty basic. I just take every result and join them together on the same day. So I want to look at a couple ways to extend the original problem, and I'm calling that evolving the original problem, and see how that affects what we have so far. So let's look at finding hypotension, which is sort of confusing, but it's almost the same word. But it means low blood pressure. And we're adding that we still want to find hypertension, but we also want to look at hypotension at the same time, because we want to know either way which one a person might be. So the rules for that is just they're hypotensive if they have a blood pressure with systolic value less than 90, diastolic value less than 60, and it was taken in the last year. And I'll add that, like, any of these numbers I'm using, I'm just making them up. Don't think that you have hypotension or hypertension or something. Like, I think some kind of standard. Anyways, so these are the rules that I would add maybe to solve this problem. Just the easiest way is just a new function that tests if a blood pressure's value is less than some value, because I was doing greater before. And then I have this thread of logic to figure out if they're hypotensive. And it's exactly the same as hypertensive, except at the very end, I just check a different value. I look at less than 90 over 60 instead. So that's sort of undesirable, just like you would think. I have two functions that are doing pretty much the same thing. So you're thinking that's a code issue because you're having duplicate code. But the other thing is that's probably more important a lot of times is it could be expensive to redo the common work, so you don't really want to keep doing that over and over again. And let's say we don't want to do that over and over again. So we're going to have to do something about getting that common part out. And there's a lot of ways, but basically what it comes down to is do the common part at some prior step, make it available to ask the two questions that are both involved, both using those blood pressures. So I'm just using a let binding here. You could have made another function that wraps those, but it doesn't really matter. And so this solves it again, but notice that the addition of hypotension as a problem made me have to go change the original hypertension problem or function. So I had to go completely refactor everything for this. And you could also think that this was very manual, that I had to figure out that I have some common state that I want to deal with. I have to pull it out myself and kind of manage where I store these intermediate results and how I'm going to get them down to all the logic branches. And like I said, things could keep getting harder. Like you could think, maybe I don't want blood pressures just in the year. Maybe I want the ones in the month for some different problems. So now I'm kind of like starting to deal with another chunk of blood pressure that I want to use for some other problems. And you're just going to keep breaking down the branches, storing all these intermediate states to try to solve all these problems. So we're going to come back to this when we look at the rules, but keep that in mind. Going on to a different style of change to the original hypertension function. Now let's say we want to filter out any blood pressures that happen with an emergency room visit. And you might want to do that because somebody could be on medication in the emergency room or in critical condition. So you don't want to say they have high blood pressure just because they're hurt or something. So the emergency room visits, they come on a different kind of fact. Let's say they come on a model we're calling encounter. And we just want to get rid of blood pressures when they occurred with that emergency room visit. Going back to that hypertensive function from before, I'm just extending it to try to deal with the new logic, the stuff about emergency rooms now. So I have a function, visits for type. It just deals with filtering encounters down by type. That's how we get the emergency room visits. Has visit just takes the blood pressure in a visit and determines if they go together. And then down in the now hypertensive used to take current date and results as an argument, but now it takes current date, results, and encounters, because now we have this other chunk of information we need to know about to solve the problem. And inside, I'm grabbing the emergency room visits out of the encounters, and then I'm taking blood pressures. I made a helper function to take a blood pressure to see if it goes with any of those emergency room visits. And then I add this remove step, remove has ER visit to the original chain of logic. And then it's done. That pretty much solves it again. But the interesting issues of this one are harder to see. But on the surface, you can tell that, hypertensive had to take a new argument to deal with new logic. That makes sense because it's a new thing we need to consider. But it ends up causing this function to be pretty coupled with the idea of finding emergency room visits so it can use it later on in this chain. And you can keep breaking that out to separate functions. Like I could have another function that makes ER visits ahead of time, but then they're going to have to come here as an argument anyways. Like you'll still have the other argument. And you could try to do stuff with closures and stuff too, but either way, you're still trying to get this information down the stack somehow. And you also see patterns sometimes where like combined BPs that in the middle, like the second part of the thread, it might want to take the encounters and do the emergency room visit logic itself instead of hypertensive. So then what you would see is hypertensive would be passing encounters through to combined BPs, and it wouldn't even be doing anything with encounters. So it just becomes the middleman. And you see that a lot of times when you start trying to compose a lot of functions together. There's a problem of wiring them together and figuring out how am I going to get an input from way up here and all the way down here in the stack. And there's some solutions to that, like one big map being passed around or some global state thing or dynamic vars, but in general, it's a bit of an issue. So I'm going to look at the rule-driven approach to try to show that rules engines help address concerns like this. And going back to the hypertension problem, I'm going to start writing some rules to solve the original one. So we have a rule for finding systolic blood pressures from results. When they have the type systolic blood pressure, we insert a fact. We're going to use fact types here, like systolic BP, to indicate that we found a systolic blood pressure. So we can use that as like a higher level model for questions we want to ask later. We do the same thing for diastolic BP. Then we have a function for combining blood pressures together. So you take, for each systolic blood pressure and diastolic blood pressure pair that have the same day, we insert a fact called BP that has the value of both plus the date. And then remember, we want the blood pressures within the year, last year, or whatever it was. So we take a current date and a blood pressure, and for each one that we find that has that same year as that current date, we insert another fact we're calling current year BP, just to mark it as, we found a blood pressure for the year, in the year. And we do that for every one of them. Current date as a fact here, that's just kind of a common model for how to do it in rules, so I'm not showing anything with that. You can imagine the external application inserted a current date. Just makes it easier to think about the current time when you think of it as a fact, just as another fact in a rule. And then finally, there's a rule to find the hypertensive, which is the problem that we were actually trying to solve in that original one. And it just takes current year BPs and looks for ones that have a value greater than 140/90. And when it finds one, it inserts a fact called hypertensive. And there's interesting things going on here, though. So the hypertensive fact that's being inserted, notice it's taken as an argument, that BP that caused it. And also notice I'm using an accumulator, because I might have more than one in the current year that is over 140/90, but I'm going to make a decision here saying maybe I don't want to just insert a whole bunch of hypertensive facts because that might not be that useful. Maybe I just want to take the newest one. So maybe that's the most relevant since it's more recent than the other ones. And if I attach it to the fact, if I have my external consumer wants to look at that, they could use that for debugging or tooling or even just to show it as like supporting evidence of why I derived this information. So instead of just saying, yeah, they're hypertensive, now you can also make a chain of the reasoning behind it, and it's kind of automatic. Like, at least it kind of flows naturally with the rule forward-driven approach. And then I have to define a query. I'm using a macro called def query from Clara. It's the same as def rule, there's just no right-hand side. But what queries do is they allow the external consumer or application to be able to look into working memory for things that they're interested in. So I'm making a query so that they have a way to get in there and look for hypertensive facts that may have been inserted when the rules were fired. Just to demonstrate just some way that you could run rules, just to make it clear how that works. Clara has a function called make session. It takes rules, and it produces what we call a rule session, which is just a set of rules and some state of working memory. And then I'm threading it along, so insert all is inserting all those facts into that session. And then I could fire the rules. That runs that loop until the rules stop, until we're at a halting state where the working memory is stable. And then we query the session to find hypertensive results. So I want to go back to this evolution of the problem, the two different branches we had before. We'll start off with the find hypotension. So given the rules I just talked about, how do we add this hypotension question along with those rules? And that requires these two rules. Well, actually, it's a rule and a query. So find hypotensive looks like find hypertensive, but notice it's looking at current year blood pressures that are less than 90/60 instead. And it's inserting a fact for hypotensive instead. And then we have a query to get that different type of fact out for the external application to grab. The cool and the interesting parts here really is that I didn't have to go touch anything to do with hypertension, which I did have to in the first example. And I also get all of anything that they share in common, like the current year BP, that's the fact they share in common. I don't have to worry about recalculating anything or where to store that intermediate information. It's already handled by the engine. So they're branching off of just two different points of the rules, and they're getting all this shared state or whatever, all this shared intermediate results that they could have. And I don't have to do any work for that. So it made extending it with a new logic branch was easy. I could just throw it off onto the side, and I didn't have to be worried about what else was happening anymore. I didn't have to deal with the branches that aren't related. So looking at the second example from before, where we were saying filter out blood pressures when they had an emergency room visit, you might have to add some rules like this. And the first rule takes encounters that have the type of ER visit, which is emergency room. And it inserts a fact called ER visit when it finds one of those. And then I go back to that original combined BPs rule, and I just add a negation condition to it, that not ER visit. And that's where I say that I don't want to consider any blood pressures for any of my logic that come from an emergency room visit, so I just put it here, and I don't have those blood pressures anymore. And that applies to any branch I ever have off of this point. And like I said, this one's a little bit harder to see, but remember I said encounters really didn't have any business with the other logic. Emergency room visits were what we wanted to figure out. And that could be a harder problem than just encounters that have this type. It could be a bunch of rules that decide how to find an emergency room visit that takes a lot of different data points, right? So But what they do is they insert the fact when they find what we're looking for. And then we just have this single fact to use, and we put it in logic where it belongs, like naturally in the requirements, and then we're done. So it's easier to add on these extra conditions because you can go deal with how to figure out this extra information on the side, and you can get it, and you could just refer to it from one of your other rules, and all the wiring about how to get it there is done for you. You don't have to worry about how to pass this encounter information down some stack to figure out how to get it to this rule. You don't have to do that. You just say it makes ER visits, this rule uses ER visits, and the engine will make sure that it gets there. So hopefully that motivates some reasons why how the rules engines can help with this kind of extending problem. And I just want to look at a little bit of how they work to make it a little clearer what's going on, and especially how that pertains to Clara rules. And we're going to discuss the Rete algorithm a little bit. And it was around in like 1979 and 80 and 82. I think there was several papers by Dr. Charles Forgy about this. And I think one of the more popular ones is this one from 1982. I think it was one of the more official. And but basically all we're trying to do is take the rules. They have conditions inside of them. We're trying to turn those conditions into nodes and make a network of nodes and have like the data flow down the nodes of the network. And that typically looks something like this. And the way I handcrafted this diagram, and it kind of looks like sort of how Clara rules would represent the Rete network. And it's a directed acyclic graph. And you have working memory. It propagates facts out to the first nodes. And every time it satisfies a node, they just propagate those matches down to their child nodes. So the very first level of discrimination across the facts or partitioning is just by their fact type. And then from there, it goes into what we call the alpha nodes when you find matches. And alpha nodes are really just extra filtering. They're only involving one fact at a time, just like, is your type systolic blood pressure? And if it is, it propagates it along. And it gets to these beta nodes, and they represent complex joining between more than one fact at a time, 2 or more. And you can join a lot of facts at a time. It can go deeper than like just 2 facts together. It could be 2 or 3 or 4. And what you're going to see is you're going to see beta nodes sort of start chaining too. They're going to have 2 or 3 or 4 beta nodes represent that, because each beta node is responsible for like one part of that join as you go down a rule. So I want to look more directly at the alpha nodes. And they're often called one-input nodes. And the reason is, like I said, they're only concerned with the property about one fact at a time, so that's their one input. Taking one of the rules we had from the example hypertension problem, this might be a little mini Rete network that comes out of it. And you see that we have working memory propagating facts to the fact type result, which is the only type we care about in this network. And then there's an alpha node to do that test of, is your type systolic blood pressure? And then when that's satisfied, it propagates it to its child nodes. And here, I'm using these red trapezoids to mean terminal nodes, which they really just represent that the rule is fully activated. It's satisfied. It's eligible to be fired. And I just labeled it with the action that it would take in that right-hand side when we fire it. But beta nodes are a little bit more interesting. They're often called 2-input nodes, and what their inputs are is that they have, on one side, they have a fact, just facts coming from alpha nodes, so just single facts. But on the other side, what they're getting is collections of facts that have already been joined. And what they're trying to do is see if they can get that new fact to join into that collection to create a collection that's one fact larger that's been joined, and then propagate that down to their children nodes. And they chain together, so they keep making a successively bigger and bigger join. Looking at one of our rules, this one's simple. We only have one join. But I'm just keep in mind it can go further. Combined BPs. It's doing that same day join between a systolic blood pressure and a diastolic blood pressure fact. And its Rete network might look something like this. I'm leaving out alpha nodes when there's really nothing, there's no alpha nodes needed. You can think of the fact type nodes, they're really just an extension on the alpha nodes anyways, because the type of a fact is still just about one fact at a time. So the beta node that I have in a square that's labeled beta node, that's the one doing the interesting work here. And it's taken a diastolic blood pressure, the facts that are matching that on one side. And then it's taken the branch that comes down from a systolic blood pressure, the facts that match that on the other side. I talked about how the beta nodes chain along in the network, and they always take the input of another beta node, but that has to start somewhere. So usually you just have some kind of dummy top node that pretends to be a beta node that doesn't have to do any join. So I'm just representing that as this first blue box that just says equals date, that's setting up that variable binding. So then when you get to the beta node we're looking at, though, when it looks at both sides, it gets an input from the systolic blood pressures and the diastolic and tries to put them together by that constraint, which is, do they have the same date? And if they do, it propagates it along to its child nodes, which there's only one, and the rule's fully activated at that point. So it's just a terminal node again. That indicates that we need to, it would be inserting the BP when that rule fires. So the other important part of beta nodes, though, is that they have memory. And they remember what they've seen on both sides. And we usually call it the left and the right side, since it has two inputs coming in. And because there's a good chance that at some point, this beta node sees a diastolic blood pressure, but it hasn't seen any diastolic blood pressures yet because they just haven't propagated through the network. But it remembers that it's all that diastolic blood pressure. And then later on, if we do get the systolic blood pressure, it looks in its memory to see what has it seen before and tries to do the joins. And that's important because the working memory is changing through these cycles, and the problems get harder than this, where you have inference happening and new facts are being derived. And you want to remember the nodes have this memory, so they're trading off a little bit of space to hold these references to things, and the benefit they're getting is time, because you don't have to recompute these values. So when working memory changes, only the path through the network that's affected by that change has to do work again. All the other paths are already saved. They already know what the work is that they've already done. So you don't have to compute both sides over again when you're trying to do the join. Putting together that whole picture of the hypertension example, it doesn't really matter if you can read every bit of it or anything. I just kind of demonstrated all those rules put together. You'd have like the alpha nodes on this rightmost side of the dotted line. You would have the beta nodes between the dotted lines, and then the leftmost side of the last dotted line is those terminal nodes. And I haven't really talked at length on retraction, but mostly because retraction is just modeled typically like insertion. So you still say, I'm going to retract this fact, and you try to propagate it down through the network. The only difference is, as it satisfies conditions, it removes itself from those beta node memories and any kind of local memory. And it removes itself out of joins, and that can cause rules to be no longer true. So it can turn activated rules into not activated rules. There's interesting optimizations that could be done around this, because when you inserted the fact, you could gather more details so that you could try to make the retraction faster. And Clara does some work around this, and so do a lot of rules engines. I'm not going to get into many details on that optimization at this point, though. For more on the Rete algorithm, I think a really good paper is this one here by Robert B. Doornborough from '95. And it was, that's about 10 years later than the original ones. I think there was some really good description of how the Rete network looks, and they made a big system out of it. But he also talks about performance considerations, and they're old now, but they still do have value when you think about evolving the algorithm as originally described, because the original description is very, very simplistic. So I'm not going to get into a lot of details on Clara rules today. There's a couple great talks already out there for that. I'm going to reference them in a minute. I will give some highlights, though. And so Clara rules is a lightweight library. It's just meant to solve the problem of complex conditional logic. It doesn't bring anything else big for that to do that. You really can think of it as just like a sophisticated control structure to drop into your application where you might have situations that come up like this, where you have this heavy business logic or whatever you want to call that. So it's not trying to be this general purpose programming environment or anything like take over your application and make you write everything in rules. Like that has kind of happened before in rules engines. The other thing is the working memory of the rule sessions. They're immutable, and they're done through persistent data structures. The Clojure's persistent data structures, so it performs well. It does some transient things to let it be mutated faster while it's in local scope. But that gives you all those benefits of the thread safety. You can look at changes to the rule's working memory state over time. You can store off different points in time when the rules were fired before you did other changes. So all those kind of benefits. And the rules in Clara have a first-class data model, which I think is an important thing. I've been showing a lot of DSL and stuff, but if you want to communicate to Clara making rules in a different way, you don't have to try to build the DSL out programmatically. they're described in terms of traditional like maps or records and things like that. And it's first class, so you can skip the DSL. You can make your own DSL. And we have made a few higher level constructs that directly generate these rules. But in general, you can generate the rules programmatically. You can manipulate them. You can build tooling on them and those sort of things. The other thing that's people probably get upset about is I talk about fact types in a lot of this, and people think maybe in Clojure that I just use maps for everything, so that's not going to work. So the Clara rules doesn't make you use classes and types to do that level of dispatch. That's an arbitrary dispatching function, and it's actually an optimization to try to dispatch on something that separates your data better. But it's pluggable, and that way it's more like a multi-method, in that it can test some arbitrary property of the fact that's being propagated, instead of being like a protocol where you're rooted on just type-based dispatch. And then the last main thing I want to point out is that Clara rules has a durability layer. It's pretty new, and the API is still a little bit in flux. We have it marked as experimental, but we've started using it in production, and I just think it's a pretty cool feature. It's where you can take rule sessions and store them out of process and restore them back into process again. And one of the key things is that when you deserialize it, it doesn't refire any rules. It just comes back again in the state that it was in before. And this lets you maybe have you might run some really heavy batching work to generate some state of working memory. You can put it offload it to disk or something, and then maybe on a service you fetch it again for a particular case, you fetch a particular working memory back into memory again pretty fast, and make small changes, fire the rules again, and then persist that. So you can make these incremental changes that last longer than just a single lifetime of one process. And there's a lot of details on that issue about some of the goals, and so I just linked it on here. And like I said, there are two really good talks given by Ryan Brush at Strange Loop and at Midwest I/O. He created Clara rules, and I think they do a great job of really demonstrating Clara and showing off its features, and he does live demos and stuff. So I left that for those talks to be seen if people are interested in that. And that's all I have.